Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Chrystian Luciano Pereira and Felipe Braga-Ribas with us today. Hello, Chrystian. Hello, Felipe.
Hi,
Hello.
Frank. Hi.
Hello.
Well, thank you so much for agreeing to talk about your very awesome article, which we'll get to here very shortly. And Christian, let's start with you as you're the lead author on this one. What's your geolocation? Where are you at?
Okay, now I'm in southern Brazil, in my city, in Bituva, Paraná.
Hmm.
I'm working from here at the moment.
Very cool. And what is your position there?
Yeah, I'm a postdoc in Observatório Nacional in Rio de Janeiro, and mainly work with stellar occultations by small bodies, by rings, mainly by rings.
Yeah, very
Yeah, yeah.
cool. Let's see. And let's see. We are past equinox and we're coming up on solstice. So, how is the weather there in the southern hemisphere where you're at?
Yeah, now we are in the spring, but looks like we are in the winter. So,
Not quite left yet.
Yeah.
yeah, it's
Cool.
cold. It's cold here.
Okay, very cool. And Felipe, how about you? What's your geolocation?
So I'm in Curitiba, Paraná, also. I'm professor at the University, Federal University of Technology here in Curitiba. Yeah.
Very cool. Very cool. So I'm in Phoenix, and it is November 6th of 2025 as we record this. And here in this part of the Northern Hemisphere, where Phoenix is definitely coming into its winter mode. But we never get too cold in the morning, and it warms up very nicely in the afternoon. And this is what brings all the Canadian snowbirds down from Canada down into the Southwest area. So very cool.
Yeah.
Very good.
Curitiba is not very far from Imbituba, so I'm also having a not great time here, even if it's spring already.
It'll
But
get
it's
warmer
okay.
soon. It'll get
Not that
warmer
cold.
soon.
We're looking forward
Not that cold.
for the
Yeah.
summer.
Very good. All right. And Christian, what do you like to do for research?
Yeah, as I said, I'm a observational astronomer. I'm work with telescopes. I observe stellar occultations. I'm specialized in stellar occultations. So since my master's degree, during my PhD, I'm working with stellar occultations, observing, analyzing data, but mainly with stellar occultation by rings. So I'm use telescopes from big telescopes from the world to analyze the light curves, to discover rings or search for rings.
Hmm, sounds like something we're going to cover here. And Felipe, what do you like to do for research?
Yes, well, also I'm specialized in stellar occultations since my PhD back in 2009 when
Okay.
I started to learn about it. And we started back there great international collaboration. I made my PhD at Observatório Nacional and Paris Observatory,
Uh-huh.
where we started this collaboration with Bruno Sicardi, the leader of this research, and with José Luis Ortiz from Spain.
Uh-huh.
So we have Brazilian researchers, French researchers, and Spanish researchers doing this work since 2009.
Cool.
Uh, Studying small objects of the solar system and doing great discoveries since then.
And they are great discoveries. Yes, they are.
Yeah.
And that is going to bring us to this very awesome APJ letter. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. The rings of 2060 Chiron, evidence of an evolving system. And Christian and Felipe, take us away.
Thanks, Frank. So, as Philip said, we are a big group of researchers. We are professional astronomers from Brazil, Paris, and also from Spain.
Cool.
And that uh, Felipe mentioned Bruno Sicardi. We have also José Luis Ortiz and a lot of Brazilian astronomers
Nice.
in this author list. We also have here some citizen astronomers. Stellar occultations is a science that we can do using professional telescopes, but also small telescopes in the
Yeah.
backyard of the people that love astronomy.
Very nice.
So these citizen astronomers contribute, and then they contribute with the science.
Very cool. Very
Yeah,
cool. It's
we
good
have
to
a
have,
lot of
good
citizen
to have that.
astronomers in the list.
Very nice.
Yeah,
Okay.
stellar occultation is a very collaborative research. So that's why we always have many authors, because all of them were fundamental for acquiring the data that we need.
Very cool. Wow.
Pleasure to have so many authors.
Beautiful.
Yeah.
Beautiful. Good collaboration. Good collaboration. Good shout out. Okay, let's go ahead and let's go.
Okay, so, well, Frank, as you may know, rings are found not only around the giant planets, but also around the small bodies.
Mm-hmm.
So we have two rings around the centaur Chariclo or Carico, discovered in 2014 by Felipe Braga-Ribas and his team. We have we have one ring around the dwarf planet Haumea,
Mm-hmm.
that was discovered in 2017 by Ortiz, José Luis Ortiz, the Spanish in the author list.
Uh-huh.
And we also have two rings around the Transneptunian object Polar.
Mm-hmm.
These two rings were discovered by Brazilians. One was the Bruno Morgado, the Nature paper in 2023.
Yes.
And the second one was discovered by me in 2023 as well.
Awesome.
2023 as well. And now, in this paper, we confirm that Chiron has three confined rings and an evolving equatorial disk. So we have now four small bodies with confirmed ring system.
Cool.
So, okay, these rings are very diverse. We have bodies at different heliocentric distance. The centaurs are about 14, 15 astronomical units.
Mm-hmm. Yep.
We have Haumea and Kawar at 40, 45 astronomical units. So it's very different heliocentric distance. Some of these rings are outside the Roche limit as Kawar rings, and at least one of Chiron I will show you today. Sometimes these rings are very confined. Sometimes the rings are more dispersed, more sparse,
Uh-huh.
wider rings with less material. Sometimes confined rings with a lot of material. So this suggests that the formation of these rings may be the result of a combination of factors, like the ejection of material, or maybe some satellite that approach too much to the main body and some fragmentations. But these are not only the factors necessary to form a ring. We need some dynamically favorable environment. Okay.
Right. I'm with you.
Okay, you can go ahead.
I'm with
Maybe
you.
giving some
Maybe we
context.
can talk a little bit about Chiron.
Yeah.
It was discovered in 1977, right? So maybe Christian can continue on this. Yeah, you want?
Yeah, I can do this. Yeah, so give some context on Chiron, right?
Yeah.
It's a centaur object. It's orbiting between Jupiter and Uranus. It was the first centaur ever discovered in 1977.
Oh,
It's the second largest one. We have with about 200 kilometers. The biggest one is Chariclo with 250 kilometers.
okay.
These two bigger centaurs. Since its discovery, Chiron has shown cometary behavior
Yeah.
with visible coma, indirect images, some occasional brightenings like outbursts. In fact, we had a big outburst in 2021. This is the last one, as far as I know.
Yep.
Some stellar occultations in the 90s, 1993, 1994, revealed signatures of additional material. So at that time, it was interpreted as confined jets or dust shells.
Ooh, okay.
In 2011, we have symmetrical flux drops again observed using stellar occultations, but now they were interpreted all together. The stellar occultations in the 90s and now in the 2011, they were interpreted all together as a possible ring-like structure
Cool.
for the first time.
Okay.
Yeah.
Um,
After the discovery of spherical rings, they saw this light curve from back in 2011, and they saw, wow, this is very similar to spherical.
yeah,
So this may
Ah,
be a ring. And José Luis Ortiz made a paper argument on this, saying, wow, this may be a ring. Here's the pole. Here's what we can think we are seeing around Chiron. But there were also other papers by Amanda Sicafuz, for instance, uh, where she explored other possibilities. So this may not be a ring, but this may be a shell. This may
okay.
be other things, right? So uh, also, well, the data was not enough to really state this is a ring. We
Okay.
needed more data.
Okay.
yeah. Mainly because every time we have a light curve from Chiron, it's something different we are seeing.
Yeah.
Every time is something different appear on the on the light curves.
Uh-huh. Okay. I'm
Yeah.
with you.
So yeah, trying to understand better, we observe another stellar occultations. We had one in 2018 that show again the ring-like pattern. So very similar with the one observed in 2011.
Okay.
In 2022, we had another stellar occultation with same ring-like structure, but now there's something more. Yeah, we saw an maybe material, a diffuse layer of material between the rings and dispersed between the rings and between rings and Chiron. So
Mm-hmm.
it's more material dispersed in that region, and this may be or maybe not related with the outburst in 2021.
Okay. I'm with you.
Okay, in this article, in this letter, we present the results of the recent stellar occultation in 2023, yeah,
Mm-hmm.
which again showed these confined structures in the same place of the rings, expected places of the rings, for the rings, but along again this layer of dispersed material, but now looks different of what we saw in 2022.
Oh, wow. Cool. Okay.
Yeah. So as I said, every time we look to Chiron, there's
It's
something different
different.
occurring. Yeah.
It's evolving. It's evolving.
Yep.
Yeah.
Very cool.
So maybe we
But
can go to figure one. Yeah.
Figure one. Okay, let's go to
yeah,
figure
Yeah.
one.
yeah, this is nice.
So we made this campaign in 2023, and this stellar occultation was crossing Brazil, Argentina, and Chile. We had large telescopes such as Gemini and SOAR telescopes, but the
Nice.
weather was not great there, so we could not observe from those large telescopes. We did observe from the largest telescope in Brazil, which is the 1.6 Perkin-Elmer telescope
Okay.
of our National Laboratory of Astrophysics.
Uh-huh.
And this telescope gave us this great light curve with lots of information with the occultation of the main body and also some other things around it. Also had detection from other sites, which allowed us to have an idea of, well, a new idea of Chiron size. Also, other not so detailed detections of these structures. So we focused on this light curve to really understand what are all those drops that we see
Right.
around Chiron. Okay.
Bink, bink, bink. Bink.
Okay, maybe I can go deeper in this figure. We can see the main body occultation in the center is very close to the 0 point. Yeah, this
Yes.
main body. This is
Yes.
Chiron passing in front of star. And both sides we can see narrow and symmetrical flux drops.
Yes.
This
Yeah.
very, very narrow. There are 3 in each side. And these are the signatures of the confined ring. They are located in about 270 kilometers, 320 kilometers,
Yeah.
and the othermost is about 40,
Yeah.
440 kilometers.
Uh-huh. Uh-huh.
Yeah, this one that you pointed is the new one. This was the first time we saw this structure.
Outer ring.
We call this key 4R, the Chiron 4 ring.
Okay, good. Thank you.
Yeah, it's the first time we saw that.
Nice. Good.
Okay, this ring is very narrow. It's very in size of about 10 to 40 kilometers wide.
Yeah.
That is this confined ring. The one that you point in 1400 kilometers is
The water.
about 100 kilometers
Yeah.
wide.
Yeah.
That's a big one. But the main thing here is this dispersed material close to the rings and close the confined rings and close to the body.
Oh, yeah, yeah, yeah. Uh-huh.
Yeah, we are, yeah. So this is indication that we have more material in the Chiron's vicinity.
Uh-huh. Uh-huh.
So we consider 2 models. We had two hypotheses to what's going on here. We tried the equatorial disk model is in the left side, and the right side we had the shell model. Maybe we can go to figure 2. We have a
Sure.
nice visual.
Oh, visuals are always good. Movies are good too.
Yeah.
There's a little touch on the observations, folks, if you want to take a look at that. Figure 2, let's go. Oh, sky projections. Okay, very good.
Yeah, I think it's better to explain. So, okay. I'm sorry.
All good.
Okay, in the left side now we have the shell hypothesis. We have here a cloud of material that distributed isotropically around Chiron. So here we have 3 consecutive shells.
Okay.
Okay. Well, this is one hypothesis. In the right side, we have the second hypothesis, the second model that we test. That is the equatorial disk. So now we have all the material flat, sharing the same plane, the same polyorientation, same plane of the confined rings.
Cool.
So yeah, you can zoom in these insets. You can see some black ellipses that are the locations of the confined rings.
Yes.
In head, we can see the boundaries of the Roche limit. So we do not know exactly the mass of Chiron, so we have this big uncertainty. And in blue are the spin orbit resonance locations. This is the inner one is the 1 to 2, and the other one is the 1 to 3. Okay, so we test both models with the light curve. Maybe you can go back to figure 1. Sorry.
It's all good. It's all good.
Yeah.
Figure 1, we go back. Now we have a little better visual of what those 2 models are, and let's go back to the light curves.
Yeah, the main point here is that when we look to the observed light curve is in gray in the left side, and compare with the black curve. This is a model. We can see that we have a gradual return of the stellar flux near to the center, near to the body. So this means that in this region there's probably little or no material. Okay,
Yeah.
so there is a gap between Chiron and the confined rings.
Yes.
And this is not we don't see this if we consider the shell model, because we already have material, always have material between the line of sight and the stars,
Yes.
because it's spherical, right?
Yes. Yes. Hmm.
So
So,
this is one reason that we are
Hold
the
on.
equatorial disk model is our preferred
here we tested
explanation for this.
those two. Sorry, Christian.
Yeah,
So here we
go
test
ahead.
those two hypotheses. Well, is
Yeah,
it a ring, is it a disk, or is it a shell? So now it's clear it cannot be a shell. If it was a shell, we wouldn't see this this flux coming back
yeah,
to
Oh,
one.
right. Because there's always something in the way. Right. Mhm.
yeah,
Right.
And now it's clear. We modeled this dispersed material as Gaussians, as we can see here, and we removed this from the data, so we can now look for the rings, the confined rings, in detail. So we first
yeah,
made this model of the dispersed material to then look through the confined material.
I'm with you. Cool.
yeah.
Good.
Okay, we can move forward. Maybe let's go to the figure 3.
Okay. Light curves, observations. There was our visual.
Oh yeah, we can just go through the table one.
Sure.
Uh, it's only the information about the occulted star and the information on the stellar occultations that are relevant. For instance, the star is very small, so uh, the drops that are not sharp, we cannot say
Oh,
that caused by the star because the star is almost punctual. And just to mention, we also have in table two, we have all the information of from the observers. So the locations they were, the setup they were using. Just to mention that, well, we all the information is there, so we can always go there and try to reprocess the data. So I think it's an important thing to have. Yeah, just to mention.
absolutely. Okay. Now that I messed that
Yeah,
up, let's just take a quick peek here at table two. So
Yeah.
this is a long table two, so we'll just show a little bit here, but we got the observers, cameras, filters. Very cool.
mhm.
You did the observations. Very nice.
Yeah, all the circumstances of the observations.
Beautiful. Beautiful.
Yeah,
Okay. So let's slide back up.
yeah. To the figure 3, maybe.
Figure three, occultation profiles.
Yeah, so you can see here optical depth profile plotted versus radial distance on the ring planes, in the same plane of the rings. So now we project this light curve,
Right.
and we can see here colored vertical bands that mark the important dynamical regions. Okay,
Cool.
so we can see in
Okay.
green. Yeah, in green is the 1 to 2 spin orbit resonance. As I said, we have a big uncertainty, so it's a region, not uh, a line. We have in red the 1 to 3 spin orbit resonance.
Mm-hmm.
So what does it mean? At this location, orbit particles in ring complete one revolution around Chiron for every 2 or 3 rotations of the body.
Yes.
Okay.
Yes.
Uh, in blue, we have the Roche limit region. Yeah.
Mhm. Yep.
So it's a boundary where we have the two inner rings. So basically here, at this distance, satellites moving inwards will fragment into small particles, maybe forming rings.
Uh-huh.
On the opposite side, we have these rings that move forward from the Roche limit
Yes.
and are agglomerated
In a
in
sense.
small satellites.
Very cool.
Yeah.
So just
Uh,
to, as Christian mentioned, we are seeing from other studies that this resonance, especially the 1 to 3 resonance, may be very important for confining the rings. So
Yes.
this is something that's well, we have some articles that are coming out that are showing that the relationship between the resonance and the location of the rings. So
Okay.
it's something that we not we we by we I mean the scientific community
Yeah.
is Hmm.
Cool. Very nice. Beautiful.
And
Beautiful.
it's clear from that figure that the Chi R3 is outside the rock limit.
Uh-huh.
Yeah.
Uh-huh.
Something that we saw also for Color.
Mm-hmm.
Very
Yeah,
intriguing.
the outermost ring of Cauer is well outside of Roche limits and
Yes.
presents the same profile that we are seeing here. There are, in one side, we have a lot of material in one part of the ring, but in the same ring in the other side, or in some region, we have less particles and more dispersed particles.
Got it. Got it.
So here we are seeing the same
Ah,
thing we saw in
okay.
Cauer.
Okay. Asymmetric.
Yeah.
Very asymmetric. Okay.
Okay, and again, we can see the broad ring, the equatorial disk. So this extends from about 200 kilometers to about 800 kilometers.
Uh-huh.
And
It's
as for equal, we see the Chi2R ring
Uh-huh.
is it's not well one ring. It may be interpreted as two rings.
Right.
The is the W shape, so it's something that's going there. Maybe it's a small satellite is that is between
Dude.
or forming this gap.
Yeah.
So something that we need to learn more about, but we see also this structure in charicula rings.
Oh, okay. Good, good, good. So
yeah, as a
precedence. Uh-huh.
yeah, the Quechua ring here in Chiron. Uh, when we saw this ring, this is the first ring observed back in 2011. It's a very it was clear separate structures, two structures very separate. So
Mm-hmm.
now we are seeing that is
Starting to resolve.
come close
Mm-hmm.
to each other.
Mm-hmm.
So that there's something different in this sense too.
It's an
It's
active.
evolving system. That's
Yeah, it's an active
Yeah,
system. It's moving.
explain the title because well in 2011 they were separated and clear. There was no broad structures. It was a clear light curve with two separate rings. Now we have this broad structure with these rings coming closer. So it's really
yeah,
evolving.
Yeah, on human timescales too. So that's even
Yeah,
nicer,
that's
right?
impressive.
We don't have to wait 100 years to see some motion here. Very
Yeah,
good.
yeah.
Very
I
good.
think that's the most interesting thing because we are seeing things live. We don't need to wait for a century to see the evolving the rings evolving. We can see it by observing stellar rotations from years to year after year. We see
Yeah.
that changing.
Yeah. It's
yeah.
very nice.
Yeah,
Very, very
for the first time, huh?
yeah. 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 Gives you a sense of the dynamical timescales involved. Very nice.
Exactly. We
Cool.
can calibrate a little bit our the simulations, for instance,
Uh-huh.
to see these things evolving
Ooh.
in this time scales because we know now the time scale, right?
Right,
Mm.
right. Yeah, that's
Yeah.
a huge piece of information. Uh-huh. Cool.
So,
Okay.
okay, so from where we are, this material are coming, I guess is maybe the main question here. So, well, we bring some possible mechanisms in this paper to explain this increase in material. One of them is the cometary outburst. As I mentioned, we had a big outburst in 2021. So
Mm.
this could be ejecting dust that to the proximities of the Chiron, and with the time, the possibly will slow settle down into the equatorial plane.
Okay.
That's one hypothesis.
Yeah.
The second one may be collisions with a small swarm of the debris. So maybe Chiron uh, cuts the orbit of a second body, and we have a
Okay.
small swarm of debris that are hitting the body and fed the region,
Yes.
or maybe a fragmentation of a small satellite. So
Okay.
we estimate the mass of this broad disk, and we need a satellite of in size of about 0.5 kilometers
Okay.
to have all this material uh,
Mhm.
around Chiron.
It's
Cool.
interesting that
So
this hypothesis corroborates with James Webb Telescope observations, because we it's a little bit to in the other page,
Yeah.
go up a little bit. So
yeah,
we have CO, CO2 down, yeah, at the end of this page. Go there.
Okay. Uh-huh.
A
Here
little
we
bit
go.
further.
Here we go. Uh-huh.
Yeah, there. Exactly.
Mm-hmm.
So we see, well, methane was detected, CO2 was detected, but not CO. And we would expect that CO would sublimate, and we are not seeing it.
Okay.
So it can be possible that this CO is still in the grains, right?
Yes.
So it is something that break it and form this form of material, and but it does not corroborate with sublimation.
Right.
So I cannot specialize on this, but it's what I see from that observation from James Webb. Yeah.
Okay. Got it.
Yeah.
Yes. It's deeper in. Right.
Yeah.
Mm-hmm. Mm-hmm. Right. Exactly.
yeah,
Episodic.
Very,
Yeah.
very interesting hypothesis that well, a satellite broke, and we are seeing.
Mm-hmm.
Uh, uh,
And you're seeing that active activity. Very cool. Beautiful.
We didn't went through figure four. We talked about that, but I think it's good to go
Yeah.
to figure four.
Okay.
Uh, there we see all the stellar occultations observed by the rings observed in 2011, 18, 2022, and 2023.
Gotcha.
Uh, yeah, when
Ooh.
we consider the pole. Or as it a ring, so we can obtain a pole, and we see the changing on the aspect angle through the
Yeah.
years, and
Yeah.
that's exactly what we need to fit all the detections. So if we don't use this pole, if we use a shell, we cannot fit these detections. They are at different distance. So when we consider that it's a ring, that's the pole of that ring, we can really see these all these detections as a ring, as coming from the same rings, right?
Yes. For
So
sure.
this is like a proof that we are seeing rings.
That are evolving.
Yeah.
Very cool. Very cool. And I think we also have we might as well show it as long as we got it up. I think we have a nice little
Yeah.
image here
yes,
of the whole system. So let's
I
take a look
forgot.
at the whole system and let's
Okay,
roll.
It's an
Bang.
artistic view made by a former student of mine, Alexandre Crispin, and with me, and we
Cool.
all see all these details as we work close to it. So maybe one day we'll see that with a spaceship, right?
There we go. Yes, yes. Oh,
Very
nice. Uh-huh. Uh-huh.
interesting.
One, two, three. Yes, here they're two very close to one another right now. So this was our W
Yep.
feature
yeah,
in the spectra. Yes. Mm-hmm. And
we can
And
see
the
the
outer
arc.
ring. Yeah.
Yeah, there is a region with more material, more narrow, is passing
yes,
up. Yeah,
Yeah,
this
the
this is
outside
it.
ring that we are seeing here, it's narrow in one side, it's broad in other side.
right. It's asymmetric.
Yep.
Uh-huh. Yes, here
Yeah.
it is
And
narrow and there it
also,
is broad. Yep.
yeah.
Uh-huh.
And
Oh,
also
beautiful.
Chiron has this potato shape. So
Mhm.
we are we have a paper in 2023 where we measured its sizes. So this was done under some hypothesis. but we will for sure have better measurements of its size, and that's very important for
Yes.
the dynamics because some works use exactly the oblateness of Chiron
Uh-huh.
to and try to see the positions of the resonance, the position of the 1 to 2 resonance, for instance, to see if it was cleared out or not,
Right.
and the position of the rock limit also. So it's another important thing to do, and we are doing that. We
Cool.
do have more data, and we do have work under that is we are doing to have a better size estimate and shape estimate for Chiron.
Right. Makes one wonder maybe if it's triaxial or something like that.
Mhm.
hmm Beautiful. That was a nice little value add to this paper. Very good. Very cool. Very good. Christian, Felipe, I want to thank you so much for walking us through your very awesome letter. Thank you.
Thank you
Thank you
for
very
having me.
much. Yeah, it's
Sure.
a pleasure to talk all the to go through all the details of this paper. It is very nice.
Yes, it
It
is. Yes,
was
it is. That's why we do these.
unsuspected to say that, but yeah, I'm proud of this paper. Yeah.
Let me go ahead and touch on a couple. You mentioned it a couple of times. But let me go ahead and push on a couple of points, and let me ask, where do you think we go from here, given the published article? Clearly, we've got some more observations in the pipe. Let me ask, what would it take to get a more accurate mass measurement of Chiron? And is there additional theoretical studies, simulation studies that could be done? So, just sort of next steps. Where do we go from here?
Yeah, okay. We have yet a new paper where we perform some models, numerical models of the particles around Chiron,
Cool.
trying to understand the dynamic environment of around the object. So this come maybe this month. Um,
Also
to
APL, APJ paper, right?
yeah, yeah, APJ.
Good.
Come.
Yeah,
So if I find it, we'll put a link to that in the description below the
Oh,
video.
great.
Okay.
It's
yeah, nice.
coming the next month, probably. Yeah, it's
Mhm.
already
Yeah.
Okay.
accepted.
Okay,
Mhm.
but to understand better the rings and if it's really evolving system, we need more stellar occultations. The
Yes.
the best case is to send a probe to Chiron,
Well,
but
that would be the best
not
case,
that.
wouldn't it?
Yeah, but so we need some more stellar
That's only
occultations
17 AU. It's not that bad.
yeah, to to better understand the rings and Chiron itself to
Mhm.
improve the mass determinations and density, the form, and yeah,
Yeah, sure.
Yeah, I think that this evolving system will be a very interesting thing for the dynamicists. So they will try to use all the information, do simulations that explain that can explain this evolving, right? So I expect that many dynamical works will be done using these as we said to calibrate the simulations, to calibrate what the quantity of material we need to do these rings,
Right.
what is needed to see this them evolving in such a small time. So I think we will see a lot of dynamic works on these, and maybe the most interesting thing is that this is not only for Chiron. Once we learn how things evolve in Chiron, we use to understand all the other rings,
Yeah,
and
yeah,
not
yeah.
only
yeah.
planetary rings, because we have rings all over the universe, right?
Right.
So and they all follow about the same dynamics.
Yeah.
So once we learn more about chiral rings, we will learn more about dynamics of rings in the universe, forming planets, forming moons, form galaxies, maybe also
Cool.
stars.
Very nice. Beautiful, beautiful, beautiful. Well, it'll be really exciting to see this develop over the next couple of years as these simulations and observations converge. And it'll be really cool to see, especially since it's evolving in real time. So very nice. Beautiful. All righty. Chrystian, Felipe, I want to thank you so much for walking us through your very awesome APJ letter.
Thank you
Thank
very much for the opportunity.
Sure. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye bye.